Hey, I have a different type of problem tonight I want to talk about. It's a fourth degree equation, and we're supposed to show that this fourth degree equation has no real roots. Now, another way of putting that is if R is a root, it would be a member of C minus R. This complex number backslash R means any complex number that is not a real number. In other words, just think of the real number line being excised from the complex plane. But in any event, now if you knew how to work a fourth degree equation, you could directly use that formula for the fourth degree result where it's worse than the third degree result. I know that. So I guess conceptually, or not practically, you could actually find the zeros and verify that all of them were indeed complex, but we're looking for a more clever approach than that. Now, notice that there is a missing x cubed term right here, which simplifies things ever so slightly. And also, you may think that this is kind of a slam dunk, the way it's set up here, because if you look here, you got x to the fourth, a really large number, x squared, a really large positive number, a fourth power is a positive number, a squared power is a positive number. So you're thinking, oh, it looks like everything would be positive all the time. And it is most of the time, but it's closer than you might think in certain cases. Now, let me just give you a concrete example. What if we chose x to be minus 1/2? Okay, something that has a pair here. So if we choose x to be minus 1/2, okay, this term right here will become what, 1 over 16? Right, remember the minus sign gets eaten up by the even exponent. Now right here, this would be 5 times 1/4, right? Minus 1/2 squared is 5 times 1/4, so this would be 5 over 4. Okay. All right, then right here, 6 times minus 1/2 is what, -3? Okay, and then this is, of course, it's a constant at 7 over 4. But you can tell this is fairly close. Now, I won't do all the arithmetic here, but you see you have this -3, all right, which is bigger than any of the other numbers. And it ends up being very, very close. It ends up being that it's barely positive at minus 1/2. And you can work that out if you want to. But this would be what, 20 over 16, 21 over 16, minus 48 over 16. And I think it's just barely over. It's just barely a positive number. So it's closer than you might think for the appropriately picked negative numbers here. Okay. Now, so the approach that we're going to adopt right here is actually, it's going to be a complete the square idea. That is, you're going to complete the square, but not really. Now, if you'll just take a look at this piece right here. See, really, y'all, the spirit of this is we would like to come up with we would like to generate another x squared term here, okay? We would like to have another x squared term there. And so what we actually do is borrow one from here. And that would leave a 4x squared here, then an x squared term here. Then we can complete the square on this side, as well as complete the square on the left-hand side. So notice that x to the fourth plus 5x squared is actually equal to this expression, because if you expand this out, you would get x to the fourth 4x squared plus 4, right? Now that's why we subtracted off this -4 right here. So we really didn't complete the square. We just wrote it in a way where we could limit this x squared to this term right here so we could complete the square. And that's really what happened on this very next line right here. Again, I just physically replaced x squared plus 5x squared with what it's equal to up here. You see this piece right here? X to the fourth plus 5x squared is equal to all this, and I just substituted it right here. This circle part right here. See, this circle part right here just replaced this piece right up here. Just replace this piece right up here. And so what happens is that's very, very convenient. The very next statement, all I did was just combine -4 and 7/4. Let's see, -4 is minus 16 over 4. That combines with 7 over 4 to give you the minus 9/4 that you see right there. But notice that we have it now where this piece right here is ready to complete the square. You're ready to complete the square right here. And we do that here. I just recopied this piece right here. Well, I just recopied the whole statement right here. Now right here, nothing's changed other than I complete the square going from here to here. From here to here, I'm just completing the square. Now notice when you write down x plus 3 quantity squared, you gen this term and this term, but you also throw a 9 into the mix that you have to subtract to correct your mistake, so to speak. All right. And now on this very next line, all I do going from here to here is just combine minus 9 with minus 9/4. Okay, and that gives you minus 45 over 4. And so we end up with this original expression. This is our original expression right here. Okay, this is what we started with, right? And we're trying to show that this doesn't have any real zeros. Well, have we done it? Well, let's check it out. What if we put 0 on here? That's going to minimize this part right here. So if you place 0 here and 0 here, what do you end up with? 4 squared? I mean, excuse me, this will be 4 plus 9. So this will add up to 4 plus 9. Again, y'all, I'm substituting 0 in for x because that's as small as this expression can be, right? That's as small as this piece right here can be. So we have 4, put a 0 right there. So we have 4 plus 9, okay, minus 45 over 4. You know, I'm running out of room here, but we have 45 over 4. And y'all, if you take a look at what's going on here, this would be 13 right here, and 13 is 52 over 4. So this would actually equal to 7 over 4. So you see, we have shown without any doubt that this expression is always positive. In other words, what we have just demonstrated is is that this guy right here is always greater than 0. Okay? Always strictly greater than 0, which means it can't have any real roots. And there you have it, folks. We did a complete the square sort of twice to get that in the desired form. But anyway, hope that helped. And I never had seen that idea before. You know, I never had seen that idea before. I thought about trying to sketch the graph by hand, but there's no way you're going to get the kind of resolution that you need. But anyway, leave some comments if you think that's interesting or you see another approach. Thanks.